Nice lineup of speakers. If you're on Zoom, please yell out your question if you have a question. We're not monitoring chat. Our first speaker is Adam Kalai of Microsoft. Tell us about succinct neural networks.
Great. So yeah, I'm excited to be here and talk about, this is joint work with Surbhi Goel, who's now at Penn, and Shyam Kakade, who's at Harvard, and Cyril Zhang, who's at Microsoft Research in New York. And this is a paper with a long title, but I think I shortened it for this talk to make it more succinct. And so I'll tell you about succinct neural networks, what they are, and how you can use them to learn interesting classes of functions. And so let me just jump right in. And please interrupt with questions. I'd rather have a discussion and not finish all the slides than faster, and I don't have that many slides. So, all right. So there's a lot of excitement about neural nets. I'm sure you all are aware. And one of the things they're not great at is learning algorithms. They're okay, but they're great at learning human-like data, but they don't seem to be amazing at learning how to multiply numbers or things like that. That's not their natural strength. So here's an example of a function. There's the lines didn't show up here, but there's the x's are on the left here and the y's are on the right, and the function is to learn which you give them two inputs, which are numbers, and your goal is, let's say, to learn which number has more sevens, okay, and just output that number. This is just some random function I gave as an example, and that's a trivial kind of learning problem for a human. And just to mention, there's this classic, I guess you'd call it a folk theorem for learning, which is that you can learn any kind of thing which could be computed by a short program that runs quickly. And basically you can enumerate all programs, which is kind of silly, but you could do it in principle. And you could find a function that maps each input xi to the output yi. And then when you find one that works on enough examples, you output at that, and you can prove guarantees that will work well. So that's sort of the monkey at the typewriter style of learning. It seems kind of ridiculous, but actually nowadays you can kind of replace it by by GPT or some large language model, and you can actually get it to do things like this a little bit. So this is actually not really like central to my talk, but I just want to throw that out as kind of an interesting twist for people to think about taking their theory things which use enumeration and imagine replacing it with a more intelligent language model like GPT or something. So you can actually type into, these days there's a system called Copilot where as you're programming, it calls GPT and tries to finish your code for you. So if you say, let's define a function called more sevens, it will put some code here, which is wrong. But it's correct code, at least. It's much better than just enumerating Turing machines. But actually, if you give it the examples I have here, and then you say, here are these examples, and here's the function more sevens, it will actually give you pretty much correct code exactly for this. So way better than enumerating Turing machines. Okay, and you could do it just to mention here, because it doesn't even have to be an efficient a problem that's in P. You could ask for, find the smallest factor of a number, smallest prime factor, which, we don't know how to do quickly. But, an average, maybe we can do it quickly on the inputs that we get, or most of them, because most numbers have small factors. So this same approach will work even if the problem is not perfectly solvable. In P, you can still do pretty well. Let me throw out another type of example, which this won't work for, which is, say, learning a parity function. In the case of learning a parity function, so the input is some vector in n dimensions of 0 and 1s, and there's some secret vector w of 0s and 1s, and the labels here are the inner product mod 2. So this won't work because the monkey or GPT would have to guess, basically, if it doesn't see these examples as input, it would have to guess, just enumerate, and have to enumerate the secret w, which is n bit. So it would be exponentially unlikely. So this approach would be, wouldn't work. It works for constant size Turing machines, but not for larger ones. So, all right. So let me tell you what succinct neural networks are. First, an analogy. So deep neural networks are, there's supposed to be edges here. Deep neural networks are like circuits. Succinct neural networks are like Turing machines. Okay. So how does that work? So I'll turn the picture on the side. So I'll put the inputs on the left here. And basically, you've got this succinct network here. that let's say it takes 3 inputs, okay, and produces 1 output. And this is going to be a constant size neural network. You can think of it like a circuit as well. It's a constant size neural network, we'll call it S, and it takes 3 inputs and produces 1 output, and you'll see why 3 and 1 in a second. And the inputs are scattered over here, and we'll pad them with a -1 on the top and the bottom. And again, this network is small, it's of size. And what we're going to do is what's called the convolutional neural network. So we're going to take this same small network and apply it over and over. And that's why we need the padding. So basically, this 2 is computed by some function of these 3. The 7.5 is some function of the next 3, the same function. And we repeat overlapping until we get to the bottom. Okay. So that's called the convolutional neural network because we're basically convolving this function with the input to get the next layer. And then we're going to repeat this. And the trick, which is different here than in most convolutional neural networks, is we're going to use the same weights, the same neural network here, S, to compute each layer. And we're going to do this T times, capital T times. Okay. So this will let us, this is called an architecture. It's one type of neural network. You could have other types. But this architecture will have some nice properties. Okay, but is the architecture clear? The only weights that you have to learn are the weights of this constant size neural network here. And then it's repeated vertically and horizontally over and over. Okay. And so that's what this SUNN is. And why is it useful? Well, I mean, what can we prove about it? So one thing we can prove is that even this simple architecture, I'm not saying it's the best one, can represent Turing machines. So suppose you had a Turing machine M and it has a bunch of states. And I'm actually going to just, for convenience, let's assume the inputs are 0, 1. And let's say all the states are even numbers. That'll make our life easy. Then we can just add the state to the input. And basically, this will simulate a Turing machine. We'll pad the input. We'll start with an input. We'll pad it with a bunch of zeros. And then we need to say, remember, a Turing machine has a head. We need to say where the head is and what's written on the tape at that place. So we'll actually add the state. So the only one that is where the head is going to be bigger than 1. That's where the head is. And the number we'll add will be the state of the Turing machine. So let's say the initial state is 2. We'll put it here at where the head is initially. Then we want to compute in the standard way where we do the tableau. We want to compute, what's the tape at the next period. And that's going to be the activations of the neural network at this layer, the first layer. And you can see that, we need to figure out, of course, where the head is and if any of the bits on the tape have changed, which is a function only of the 3 numbers, 3 activations adjacent. And that's why we have to pad it with the -1 so that we know what we're talking about. That makes sense? Same thing. And we repeat for T periods. If the final halting state, if we call that 0, then once we hit the halting state, all the numbers will be just 0s and 1s, and then we won't even do any updates at all, and it'll just progress. And T here, capital T, is the number of periods that the Turing machine can run. So as long as the Turing machine runs and completes and halts in less than T steps, this will be a faithful simulation of the Turing machine. So basically, you can efficiently convert any constant size Turing machine to a neural network that's also constant size, but bigger, that will, on any input which the Turing machine halts in time, let's say the runtime of the machine on X is less than T, this will give you the same values as the Turing machine. And then there's a lot of messy details in this paper, I have to be honest. So I'm just going to try to give you like a clean version in this talk, but I'm not going to go into all of the details. Like, for example, you can do a lot of cheating with with very large numbers and stuff like, and just say we're not cheating. The weights that the numbers we're using are all constant size and in the weights of the neural network, and this can all be done in polynomial time.
So Adam, if you compare clean models for which you can make the same statement, how would you rank them in terms of cleanliness? Right? If we had some, a graph of the plot of the power for small values of the size, like which graph would look smoother?
Clean, say it again.
No, I'm just saying that you look for very clean models if you want to extrapolate from small behavior, empirical behavior, small size to bigger sizes. So how does this rank compared to other models?
Do you want to do something from small size to large size?
So I'm not attacking that problem. So I'm not attacking the problem of out of distribution learning where the training set is in one input size and the test set is in another input size. That's an interesting problem, but we're just doing classic learning where the distribution of input sizes could vary. That's a nice thing. This will work as long, you could definitely have input sizes in your test set that you've never seen in your training set because your distribution could be big inputs.
My question was mainly in the context of other Turing equivalent models, like, a game of life and things of this flavor. How does this compare to them in terms of
what?
In terms of how clean it is, or
clean? I mean, it's not. I don't know how clean you think it is, but it's very relevant because it's a neural network. So the game of life, like neural networks, are being used a lot, and they've been this stochastic gradient descent. So that's why we're doing it this way, is because neural network architectures seem to be very relevant. But I love the sort of the general question.
So far, you've shown us the equivalence of these neural networks, but you haven't said yet how you're going to train this thing.
Right.
I was just going to ask, like, do training algorithms actually find networks that look like simulations of Turing machines?
Right. These are good related questions.
Yeah,
So
I guess
I'll jump out right away and say that I don't have like a great algorithm that is awesome in practice. We haven't implemented for this at all. This is a new architecture that we're proposing. But you can prove that some ridiculous algorithms work, and it's an open question to find a good algorithm that works in practice. But a lot of these statements still kind of tell you something about the limits of what's achievable in a representation. So it's well known that neural networks are like circuits, so they can compute basically any function, and that's a useful statement. If you took a linear classifier, it can't compute every function, so you kind of understand something about the limit of what it can and can't compute. These succinct neural networks, which basically just for Shafi, they have a fixed small constant size neural network here that's repeated in a convolutional way. So that this is the input tape, you repeat the small network, and then you repeat that same thing layer by layer, and this computes the tableau. So anyway, so that these are not limited in the same way.
So when you say it's repeated, the weights are shared?
The weights are shared. There's only one set of weights here, which are the weights of S. But the activations are not shared. These are activations, and you don't have to store all the activations. You just need to complete the activations on one layer. You just need to know the activations from the previous layer.
So they are trained. The activations are trained also.
No, so activations. What I mean by activations are there's the inputs, and then there's the weights of the neural network, and then this thing here is an activation. It's the output of this small neural network on these three things, and that call it the activation, whatever call it. That's a number that's derived. It's not trainable. It's just a function of the weights here. And that in a normal neural network, you'll do gradient descent to learn the weights here, so that finally the outputs look like what you want them to look like.
So really, at this point, we should think of it as like a standard Tableau unrolling of like Turing machine computation. Right. Now you're like, think your hardware is like a neural network.
Exactly. And actually, I really don't think that this is, first of all, I don't know why 3x1 would be the best. And also, I really don't think that a neural net Turing machine would be the best way to do this. If you ask the computer to optimize the weights, it probably wouldn't do it in a Turing machine style, because a Turing machine is very limited, where only one of these numbers changes each time. That's very inefficient. But if it could optimize the weights, then it could be much better.
But whatever weight you give, you can simulate the system efficiently. So in some sense, it's implicitly a Turing machine.
Yes, every Turing machine, every one of these you're saying can be simulated by a Turing machine.
Right.
Right. Good. Yes, it's equivalent in that sense. Yeah. But the Turing machine way of doing things is highly non-parallel, whereas these convolutional neural networks are typically much more parallel. So I would hope that if you had a problem that was parallelizable, it would actually find a much faster solution than a Turing machine.
But now you mentioned gradient descent. You couldn't possibly do any kind of gradient descent with this model, right? Because you're using, how do you compute the gradients?
You can do it. So let me do that now, because I think that's what a lot of these questions are asking about. So how do we learn one of these things? Well, if you could learn one of these, first of all, you could learn algorithms. So you've got this succinct network with a bunch of weights, which are weights on the edges here, which are not really coming out. And you only have to learn a constant number of weights, which is good. So just as a, I said I gave that weird sevens example, but multiplication is something a lot of people are trying to get their neural networks to work, to learn, and it doesn't work, where the input is, each input xi is a pair of numbers and the output is a product. Okay, that's really easy. This, in principle, if you could learn succinct neural networks, I'm not saying how, then that would work. Shortest path, you could do all kinds of cool problems where if your inputs were graphs and edges, you could find the length of the shortest path, and you could learn that from examples. Okay. Similarly, as I mentioned, that smallest sum factoring problem, you could learn as well as the best Turing machine on average. So it was an average case problem on that distribution, you could learn as well as the best. And parity functions, not quite, as I said, because we'll get to that later. And I'll just kind of, there's a trick we're going to need to do to be able to learn functions that have like a secret that's n bits long. But as I've described it now, that's not in the category of the things we can learn. And so, what can we say? Again, I'm still like stalling on this question, which I'm not going to have a great answer to, of how we're going to learn them. But if you could optimize over small neural networks, then let's just notice that would work for learning. So, in a sort of standard learning statement, you could say, look, if the Turing machine has a small constant k, and t can be whatever it is, the runtime of the Turing machine, then with high probability over m examples drawn from some arbitrary distribution d over labeled examples, what you can say, this is a standard learning result, says that the empirical error on the training set, which we call error hat, is close to the error on the test on future examples from the distribution, the generalization error. And formally, that's just the probability that if you ran this network with a given small network S, the probability that's off compared to the error in the training data. And those things will go down very quickly, like 1 over root m. Okay, so what this means, even forgetting the math, is that it makes a lot of sense. If you could somehow magically optimize these things, it would make a lot of sense to try to get low training error. And then if you did that, if you could get low training error, this would all magically learn all these algorithms that we're talking about. Does that make sense?
So the examples are actually basically like parts of the computational bubble.
No, so great question. So it's not that we're illustrating how to do the Turing machine by showing the internal states and the tableau. We are just giving inputs and outputs. And we are trying to match, this function is trying to match the outputs. And if you could do that, if you could find, first there exists a small neural network S, and then if you could find anyone that does such that it does match the outputs, then you get a guarantee that its performance on future examples will be as good as its performance on the training data. So therefore, trying to minimize your training error is a good way to generalize to future examples, or just as well as the best Turing machine. And as Russ is pointing out, getting better than the best Turing machine. But so really, it is going to match the performance of the best Turing machine.
And you do this by, this is exhaustive search of all the.
Good. So I have not. I'm still stalling. My next slide will have a teeny bit about that, but I don't have the answer. What's that?
So you really want basically so what you are optimizing for is that at the beginning you have this standard input, and at the very end you have this you just want to find out actually what should be the convolution.
Exactly. That does as well as possible. That that's as many inputs to correct outputs as possible.
So there must be some, because you can simulate an arbitrary Turing machine, an arbitrary Turing machine can have arbitrary input output behavior.
Right.
There must be some hidden constant there that kind of depends on the precision or something.
Depends on the number of states in the Turing machine.
Depends on the number of states, but then you're going to where you still have just these like, oh, do you need more hidden gates?
Yes,
To
these are
simulate
great
a larger
questions. Yeah,
Turing
the
machine?
number of layers of this neural network depends on the runtime of the Turing machine, capital T.
Oh, no, but how about just the layers?
Yeah, I need to pad the height. We pad it with a bunch of zeros so that.
I mean, the purple S. The purple.
Yeah, the size of S depends on the number of states. So if you, yeah, so then the size of S is constant, but that's a bigger constant than the number of states in the Turing machine. The polynomial states.
So this dependence on T means before you build your Turing machine or neural nets, you need to know some
The runtime.
on runtime.
Yeah, I mean, you
And
could have.
suppose you had an average runtime.
You could have a neural net, you could, it would be non-standard, but you could easily have an architecture where you keep running until something happens.
Yeah.
I guess you could do something like that. Because this is and I don't know like whether that would be practical or not, but you could keep running until helping configuration. But I don't know. Yeah, there's definitely room to improve. This is kind of like the simplest one where you have an upper bound.
So follow up, in the optimization process, you could assume something about T, right? If you,
Yeah,
like you
so
suggested.
we assume that we know T, or that we're given an upper bound on T, and then you could do a meta search over different T's if you want to.
No, but if you just, like you suggested, do something, like you run until something happens, can you optimize this
In
process?
principle, you could run it until something happened if you knew the correct neural network, but when you get a bad neural network, then you run it could just keep going forever. So you would need to kind of you would probably do that over example. It would get even messier, but I think you could do something. I think there's tricks here. Right? You guys maybe are seeing things that I'm not, but I think it's possible to get a better average version than this crude version. I'm doing average case where it's like, give me an upper bound T, what's your best average performance? But you're saying, no, let's actually get something which on some examples is allowed to run longer, and other examples will run shorter, and we're going to bound it. So I think that would maybe it makes it.
It's just like a conversion between the mathematics point of view to a computer science. Saying somebody proved there existed T. They don't know the algorithm.
Right.
You'll find it. I suppose.
Yeah. Questions? Yeah.
Show us how you train it.
I'm stalling. I'm just hoping there are more questions. Oh, I would have loved to tell you. Okay, so well, I think you all know how I'm going to propose training it, which is not going to make anyone happy. Which is, okay, so we really do the slide. We're going to, put the monkey to work. And the monkey is going to choose random initialization for this small neural network, and can choose, I forget if it's from integers or something, but it's a small set. You can just choose these discrete initializations from a small random set. And then I threw this in there to make it look more practical, but you don't actually need it. So in principle, you might also do gradient descent after the monkey's put its weights down. And that might make things better. I mean, if you already got the perfect weights, that wouldn't change anything. But gradient descent does kind of magic. Like if people had said, just do gradient descent on large neural networks, and that will do really cool things, you might or might not have believed them until it started working. Here, there is a major problem, which is that the gradients are quite large. So you were asking about this before. So like it's a function, you can take the gradient. And it's not actually hard to compute the gradient, but they compile, they kind of explode, right? The gradients get larger. Like if you take a big step, if you take a big step in the direction of the gradient, the function is going to change wildly. But you could take a really small step. If you take a really small step, then the function won't change wildly, but then you'll need more examples. So all the theory says you only need a constant number of examples to learn this thing. I think if you're going to take like small steps, you probably need a polynomial number of examples. Will it work? We have not implemented it. I'm glad I'm talking about it before we implement it. I know. Maybe it will work. I mean, I do have a reasonable justification for this, which is compare this to gradient descent on a fully connected large network, which has to learn this computation, which is polynomial size. So it has to learn all the weights, and the monkey has to get lucky, even luckier, because it has to guess kind of the initialization. It has to guess the whole circuit, right? And gradient descent may help a bit, but you're just,
But you're each, okay, but how the circuit depends on each weight is actually simpler. Here, you're reusing the weights.
Yeah, there's a
So the function
computation.
of the
There's a
weight.
computation. Like I didn't do the math here,
Yeah.
but you can do you can do the computation, and it's a standard, relatively standard, because both convolutions and recurrences are pretty standard, and the way in which it depends on all that, like these, you can do the math either yourself or there's automatic differentiation libraries that will take the gradients for you. And
Okay, so what I'm more worried about is like numerical stability.
exactly, and that's what I'm saying about the I don't well, you would definitely need to take a small gradient step, but you're worried that even the gradient itself will be way too large. I mean, this is optional. No, but it's a great question. Like I'm excited to actually try to implement it and see if this does better than, you know, what you would compare what we know doesn't work, where you have a huge circuit and a huge neural network. You randomly initialize it. It looks nothing like the function you're trying to learn. And then it does its best to generalize, and it kind of works, but not great. Or in some cases, you know, there might be some advantage. There might be some hybrid one, which is in between, where you get some benefit. I don't know.
Just to make sure I understand, so you're saying that the standard, the second part of the slide, this would be like exponential in the circuit size, and the first part, the one is
Exactly. Exactly. Because, you know, if you have to guess a circuit, right? It's ridiculous to guess a Turing machine for multiplying numbers, but it's even more ridiculous to guess a circuit. Now, I can't prove, and you could also potentially use GPT somehow. I don't know. You could try to do something smarter for sure. But basically, I was trying to be careful here. I can't prove that this thing won't work for regular neural networks, but for sure, the same proof, if you try to do the same proof approach, and you say the monkey has to get lucky, the monkey has to get really lucky with circuits. And with regular ones, my hope is that, you know, you don't even have to choose integer initialization. You can choose some continuous ones and do gradient descent, and maybe it'll work at least as well as it does down here.
In fact, I was thinking about your random, why random initialization? I mean, random, yes, but the question is whether it's totally random or something that's related to the problem you're trying to solve. Since you know
Exactly. Exactly. And that
in the case where you know a time bound,
Yeah,
it's not
exactly.
a completely unknown.
Exactly. And they have there's a lot of papers that try to learn how to initialize neural networks well across problems. And they I still don't know why that works, but it sort of works. Exactly.
Specifically for a problem like this, where you know the structure, you have a time bound on it.
Right.
There might be some randomness that will jive well with the problem itself.
So yeah, if you did this a lot, it's just, I mean, basically it's another way to write a program, but not in a programming language like Python, which GPT-3 can do kind of well. But in this weird neural network representation, which maybe computers could also learn to do, they can write code in Python, which is kind of amazing. Why couldn't they write it in this other numeric format, which might even be more intuitive to them because, or I don't know, but, you know, it's more numeric. So that's a good question.
Is there like a hypothesis associated with this, like along the lines of the uniform distribution over circuits is an interesting object to search? There's some non-negligible probability that when I draw a uniformly random circuit and do that repeatedly, maybe I'm covering the space of circuits well enough to.
Are you talking, when you say a random circuit, are you thinking of the circuit S or the circuit for the whole?
I'm thinking about the circuit S1, the Succinct circuit, and then has anyone tried de-randomizing this hypothesis? So like if we have circuit lower bounds, then maybe we can go run initializations of these things.
Well, yeah, for sure they're not initializing actually randomly, right? When they initialize their networks, they're pseudo-randomly initializing them. Right, because they have something to do with. But
then they're not.
I don't
So there's this lottery ticket hypothesis, right? Like which seems related to this. Has anyone looked at de-randomizing it to say if you have a provably secure pseudo-random generator and you assume the lottery ticket hypothesis, something like this could actually work pretty well?
I don't know. That's a good question.
So I'm looking at the statement of the theorem, and I think I don't understand what it means.
Good. Oh yeah, sorry, it's not very clear. It's not very formal, first of all. So what I'm saying is we're going to pick a random initialization. Let's even drop the optional gradient descent thing for a second. So if we just picked a bunch of random initializations, and for each of them we saw how close is the output of the neural network to, with this circuit S, to with this small, this small neural net S, to the labels of the labels that we have through the training set of XY pairs. And we see which, and then we do this a constant number of times, and we see which one of our S's, our random initial S's, gave us the best fit to our data. With high probability, one of them will match the best Turing machine of with a constant number of states and the fixed T1, T1. Does that make sense? And so, yeah.
I guess the question is like how many you need to pick as a function of the states.
Log whatever. So if you want to get, if you want this to work with probability 1 minus delta, I just did it with constant probability. But if you want to work with with probability 1 minus delta for any delta, then you need to order log 1 over delta.
Well, okay, but that's again like the hidden constants involve the number of states in the Turing machine.
Yeah.
Is it just exponential or is it?
Oh yeah. Well, you see, if you have S states in the Turing machine, then you might need like an S squared.
Yeah.
It depends on how exactly you represent your Turing machine. If it's just like one state goes to one state, then you need to say S. But it's basically like you'd expect with the number of bits you need to write down the Turing machine.
So does the step size appear in the statement of the theorem?
The step size of gradient descent?
Yeah.
No. So for the theorem, let's ignore this optional thing. Maybe I shouldn't put that in there. It's confusing. So for that's why I wrote optional. But let's say the step size is 0. So we don't do gradient descent. We just pick a random one. So the theorem is that it's a monkey at typewriter's theorem. It says, look, if monkeys keep guessing small networks, it's basically encompasses it's at least as large as the set of small Turing machines. And so this is a very easy theorem. So.
The monkey's really the star of the show.
Yeah, definitely. Sorry, so this is a trivial theorem, but it still may be interesting. And then I just threw in this thing to confuse you all about. Maybe we could do gradients, or maybe we could use some other smarter initialization, like Jeffrey was saying, like GPT or some more intelligent way of setting those parameters. So this also kind of is confusing when you think about what to do with it in this model of learning. So it's a bit different than the standard pack learning or agnostic learning. So basically, we define a model of, it's not pack learning, we have to define a new model called probably algorithmically optimal. So basically, we're saying it's, or probably approximately optimal, but also defined. We're saying that a learning algorithm is nearly optimal. Instead of comparing it to classifiers, which is the way pack learning or agnostic learning is done, we're actually going to compare it to learning algorithms. Because like a classifier, like a neural network, could be huge. GPT has 175 billion parameters. The Palm language model has 520 billion parameters. The code that they use, though, is very small. Like the amount of code to the description of the GPT-3 learning algorithm is much smaller than the neural network itself. So it makes sense to compare yourself to short learning algorithms rather than all classifiers. Does that make sense?
It's like uniformity.
Yeah, exactly. So we're defining this, which I don't think has been defined, but maybe Dr. knows. Seems very natural.
So one subtle point, I guess, is you're comparing the error of your algorithm on the validation data to just the error of the learning algorithm on the
we get bonus validation data, which you can use. We need that. We can't do this without bonus validation data. We can't just train our algorithm on the same training data and say we're doing as well as the best algorithm. But if we give ourselves a little bit of extra validation data, then we could, I mean, again, you could, the algorithm from the first slide, the trivial algorithm of enumerating programs would work here. Basically, you enumerate all programs, you run them on the given training data.
When you talk about error, you're talking about actual error, not error on the training.
Right, exactly. Future error on generalization, on future generalization. That's what the validation data is useful for. So this is another trivial to achieve thing by picking random Turing machines or random programs, running them, all the ones that completed in time t, and then taking the one that's best in the validation data And we can prove trivially that that will achieve this sort of probably approximately optimal learning for, and then we define it for, this is just, we're doing it in this case for all Turing machines, but this notion might be kind of interesting in general as a complement to pack learning, which is, or agnostic learning, which is usually defined for classes and functions. That makes sense.
So I don't understand what A is a traditional algorithm?
Yeah, A is a learning algorithm. So in learning, there's like a confusion between terminology typically where there's this notion of a classifier. And a classifier, I think of as like the neural net, the thing that's doing the classification. There's the learning algorithm, which outputs the classifier.
Yes.
Sometimes people call that a
That's
classifier too. Yeah, A is the learning
So
algorithm.
A is the no.
So A takes the training data as input and outputs a classifier, which is a neural net or circuit.
Yeah, which is an error.
Yeah.
Actually, like maybe training data, because if you have like a program like binary coding and stuff, and actually like moves like random is basically garbage. So there are just like only like few validators actually which that function is interesting.
We're taking, we get, it's not shown on this slide, but we get training data from the true distribution. So we're using real world data for training. So we assume that we have problems from some distribution of problems that we care about. It's an average case kind of thing. We got a bunch of problems from that distribution and we want to do well on future problems from that same distribution. If we had to make up, I see where you're going, if we had to make up our own problems, then maybe it wouldn't even cover anything interesting. So you're not getting the risk guarantees on all future problems, just that from the same distribution as our training data. So, and this is a generalization of pack learning. You can show that if you can pack learn a family of classifiers, then this thing, which learns the algorithms, should in particular include the algorithm that pack learns that family, so it'll do as well as that and maybe better. So kind of, you can draw a picture and say, okay, in the world of classifiers, there's all classifiers in your family. There's the, and then you can draw the accuracy on the y-axis, the Bayesian, Bayesian, they call it the most accurate classifier, but that's ridiculous. We would never be able to optimize over all circuits. So then there's the ones that are output by algorithms, efficient algorithms, and that's a smaller set. And so we want to just compete, our goal is to get accuracy near the best efficient algorithm, which is still super hard. But as I kind of illustrate here, these are programs for learning. They're much smaller than a program is constant size, and they're much, much smaller than the classifiers. Yes. But I'm so happy that I didn't have enough time to go into all the details because it's a mess. But does anyone want to stall me longer than that? All right. So okay, that's just a formal version of what I did there before. And then okay, so the trick for learning parity or any learning problem where there's a hidden concept, again, that's not a constant size machine. But fortunately, Abbe and Sandon, there's a nice, very beautiful paper they had where they showed something really surprising for a lot of us. So how many people here know what statistical queries are? So yeah, so you can't learn parities with statistical queries, and yet they proved that you could actually learn parities with stochastic gradient descent, which is a standard way of training learning algorithms on a training set, if you have a very specific and hard-coded learning algorithm in your circuit. But so the surprise was that everyone thought that neural networks were a statistical query learning algorithm, that you could approximate the neural net gradient update by just averaging over training set, and it shouldn't be that sensitive. And the whole catch, the funny thing, what stochastic gradient descent does is it works one example at a time. And that does actual magic. A statistical query algorithm doesn't get a labeled example, one labeled example at a time. It only works in aggregate. Whereas stochastic gradient descent, which we thought, oh, stochastic gradient descent is just a speed up of the algorithm that you might want to do, which is run over your whole training data, average the gradients, and then that would be a step. But actually, stochastic gradient descent is in some ways more powerful than this averaging algorithm. And that was what they showed, is that actually you can learn parities if you do stochastic gradient descent. Their algorithm will bake into the weights of the neural network Gaussian elimination, the algorithm or whatever algorithm you need to learn the problem. So it's kind of a cheat, but not really, but it still makes this point. I still think these results are useful because they help you understand sort of limits and what things might be able to do. And it definitely changed my perspective on what stochastic gradient descent is. It's not just a statistical theory algorithm. Okay, so fortunately, I don't have time to really show you the details of how that works. It's ugly, but it has some math, and it's like what's connected and what are the weights and what are the edges and everything. And actually, my edges aren't even showing up. But basically, for our construction, it's simple. I'll just talk about the architecture. So the architecture of the neural network, it doesn't have to implement their particular trick or our particular trick. The architecture just says in addition to this t-fold repetition of this small convolution and the layers, we're going to have one additional layer, which you can kind of think of like, well, it's just one layer, and it's got it's m by m times n large, so it's got room if you need to store all the training data. Okay, so that's how big it is, and then it'll actually have an extra t zeros at the end, and then there's edges between here and there's a bunch of edges, and you just start with weight 0 on them. And so the architecture is you start with this network with a bunch of edges of weight 0, and then you have this repeated thing, and you can prove that is capable of representing. If you do stochastic gradient descent in our construction, the way it might work, which is probably not the best way, but is it will actually memorize the inputs and the labels in the weights of the neural network in some kind of crazy process, and then run the learning algorithm once it's seen all m inputs. So I definitely don't have time to go into all the details. So basically, there's a few things here that might be interesting. One is this idea of instead of thinking about pack learning, thinking about competing with learning algorithms. So a family of learning algorithms, which you could actually, not just neural networks, you could think about that for, I'm trying to learn your old school SVM with a kernel and a bandwidth, a parameter. If you have a single parameter to learn, it's pretty easy. So you can try to learn as well as the best learning algorithm in the family, and it could be any family. In general, and that's what this point is, you want to learn algorithms. In general, there's a trend in machine learning to learn algorithms rather than just classifiers. So we kind of went up one level in abstraction, which is exciting. I'm curious if there's anything you can say in complexity theory, wherever you might use enumeration in your proofs. You say, well, that I used to think that was ridiculous and just a crutch that I needed to prove my theorem. Is there some possibility that I could use an intelligent language model, to train the data or something to make it seem much more plausible? Or could there be a theory of these things? I think it'd be really interesting. And we give a particular architecture here, which is recurrent and convolutional, and I think it'd be really neat to try it out and see if it works better for these algorithms problems than as a standard. Okay.
Questions? So yeah, actually about this last like a recurrent architecture in addition to this. So I was thinking sort of to solve like what Shafi was saying, where you have too many layers. You could, if your hidden state was like one additional bit that you just write to once. I mean, because when you're in a halting state as you slide that window over, you could just put a 1 on that and then define your architecture to be one that halts the recurrence.
Yeah, I see. You're saying
it's like
you
just
think
the
you can make Shafi's
definition.
thing work by just saying the number of repetitions is not fixed in advance, but you just keep going until you see a 1 somewhere or some number that's very close to some constant, and then stop at that point.
And it's maybe a bit more, but I think it's like a bit more natural to think about, because it doesn't like the number of layers is whatever is inside that small window, but then just like how in RNNs, you don't call every recurrence a different layer.
Right. Yeah. You don't think of these as separate layers. You just think of it as a recurrence. Yeah. Thanks.
Back at 10:30.